Good morning, everybody, and welcome to the calculus lecture for Thursday. We are going to finish up our fundamental theorem of calculus, part 2 today. Hope the quiz went well, and we'll just do a quick review of the fundamental theorem of calculus part 1. Then we'll do fundamental theorem of calculus part 2, and this is the part that you're going to use a whole lot more. We needed part 1 in order to prove part 2. Just as a heads up, next week we do have a normal week again, but Monday and Wednesday we're going to go over section 4.5, and that's going to round out, that's not quite the end of chapter 4, but it's going to round out what we're going to do. And then Thursday we're actually going to do review for the test the following Monday, and the test is going to be over sections 3.7, 3.8, 3.9, so a little bit of stuff we didn't cover in chapter 3 in the previous exam, plus the first part of chapter 4 here. And I'll do a review, so you'll get a chance to kind of know what's on there and what do you still need to study. You'll have some review problems that you can go over, and I'll give you some solutions for those, so you can kind of double check yourself there too. Okay, but that's not, the review is next week on Thursday for the exam the following week on Monday. Okay? All right. Let's see. So let's just recall that, well, because this is so important, let's put it in red. So section 4.4, fundamental theorem of calculus, part 1. Okay, you probably heard me say this yesterday. I generally abbreviate this FTOC, Fundamental Theorem of Calculus. What it says is that if, I write this in blue, if you have a function that's continuous on a closed interval, and you let capital F be the area from A to X under little f, so it's an area function from A to X. This area is capital F. Okay, then 3 things turn out to be true. I didn't state it this way, but that function is actually differentiable. Okay, and because it's differentiable, it's continuous. So I'm just going to write that. It's continuous and it's differentiable. But the important part is that the derivative of that area function is the original function again. Okay, that's where we get the 3 exclamation points. The derivative of the area function, the change in area, is the actual original function. And if you remember, the reason for that, which kind of makes sense if you visualize it, is that a small change in the area function divided by the width gives you the height, and that's, dividing by the width is kind of what we're doing when we take the derivative. Okay? So this makes sense, and one thing that resulted from this is that all continuous functions have antiderivatives. Big F is an antiderivative of little f, because when you differentiate it, you get little f. All right? So that was FTOC part 1. Let's take a look at fundamental theorem of calculus part 2 now. Fundamental theorem of calc part 2. Okay, what this says is that if you start with a continuous function on a closed interval, and if f is any antiderivative, we know little f, we know a continuous function has an antiderivative. So if you take any antiderivative of little f, then to calculate a definite integral, all you do is plug in b minus Find the antiderivative and plug in the upper limit and plug in the lower limit. So in other words, what this is saying, this is the powerful part about this, is that if you can find an antiderivative for the function that you're trying to find the definite integral for, if you know an antiderivative, use it and just plug in these numbers and you're done. There's no rectangles, cutting up intervals, taking limits of Riemann sums, none of that. If you need to find this area, the area from A to B under a function, if you can find, and that's a big if you can find an antiderivative, then you're good to go. You just plug in points, and that's it. Okay, let me show you what I mean by that. Let's take, if you open to page 284, okay, I want to take a look at a few examples here. So let's take a look at number 5, for instance. This is asking me to find the area from 0 to 1 under 2x dx. Okay. So earlier, the way that I would do this, before we had the fundamental theorem of calculus, if I said do this, you would have to draw the function. Okay, and then to get this area, before we would cut up the interval, we would draw rectangles, find the areas of those rectangles as a Riemann sum, and then let n go to infinity. Because this is a line, we can do it using geometry, but this theorem is just saying if you can find an antiderivative for that, you're golden. So what you do, what is an antiderivative? What's a function that differentiates to 2x? Well, that would be x squared, right? So what we're going to do, according to this theorem, is we're going to plug in 1. We're going to take x squared and we're going to plug in 1 minus what we would get when we plugged in 0. So in other words, 1 squared is 1 minus 0 squared is 0. That's just 1. That's the answer. Boom. We're done. Wow. That is amazing. Now, to be able to do this efficiently, what we're going to actually develop a notation here. When you find an antiderivative of the inner thing, we're going to write it, and then we're going to draw a vertical line, and we're going to list these two limits of integration here. And what that means, this is just an intermediate step that says, here's the antiderivative. I'm going to plug in 1 minus I'm going to plug in 0. So we're going to have a notation here that when you find that antiderivative, and I want to plug in A and B, I'm going to write it like this. And what that means is the next step is I'm going to plug in B minus I'm going to plug in A. Okay? Let's do that with another example here. Just 1 second. Okay, let's look at problem number 8 for a second. Okay? So we want the area from 2 to 5 under the function negative 3v plus 4 dv. Okay, remember, doesn't matter what letter is there. If these are numbers, this is just going to end up being a number. It's just an area. So it could be x's or b's or whatever. So what the fundamental theorem of calculus tells me is that I need to find an antiderivative of f. So let's think about this for a second. What's a function that differentiates to v? Or if it helps you to think of x instead, think of x here. What's a function, forget the negative 3 for a second. The negative 3 just kind of comes along for the ride. But what's a function that differentiates to x? That would be 1/2 x squared. In this case, we're using v. So 1/2 v squared, right? If you differentiate this, 1/2 v squared ends up going back to v. Okay. Plus, what's a function that differentiates to 4? Well, that's just going to be 4v, right? If you differentiate 4v, that becomes 4. So this is, right here, our antiderivative. And what we're going to do is we're going to plug in 2 and we're going to plug in 5. We're going to plug in 5 minus plug in 2. And I'm just going to use this notation to say, hey, we're getting ready. We're going to plug in 5 and we're going to plug in 2. So be watching. So let's clean this up just a little bit before we do that. We've got negative 3/2 v squared plus 4v, and then we're going to plug in 5 and plug in 2. So let's plug in 5 first. Okay, so plugging in 5, we've got v squared is 25 times 3 is negative 75 over 2. Plugging in 5 here gives me a plus 20. So I just plugged in 5. Minus, now let's plug in 2. So we get negative 3/2. This is going to be 2 times 2 is 4. So I've got negative 12/2 plus plugging in 2 here gives me 8. Okay, got it? So we're just plugging in 5 minus plugging in 2. Let's work this out a little bit more. So we've got negative 75/2 plus 20 minus minus is plus 6 minus 8. So negative 75/2, 26 minus 8 is going to give me 18, which is 36 over 2. Numbers here aren't that beautiful, but that's okay. And then if I have negative 75 and I add 36, that's going to give me negative 39, I believe. Negative 39/2. Okay? But the amazing part, the fundamental theorem of calculus, what's so amazing here is that this step right here, just find an antiderivative and plug numbers in. That's all we have to do. That should be pretty amazing. Pretty mind-boggling. No rectangles, no anything. Just find an antiderivative and plug in. Let's look at one more example, and then I'll say a couple more things here. All right, let's look at number 14. All right, so number 14, I want the area from negative 2 to negative 1 under the function u minus 1 over u squared du. Okay. One thing that happens in a lot of these problems is that you start to get negatives flying around, so please be very careful of your parentheses. All right? According to the fundamental theorem of calculus, my job is simply to find an antiderivative and then plug in. So in order to find an antiderivative, let's get that thing in a slightly nicer form. The u is fine, but I need to make this u to the minus 2 so I can kind of use the inverse power rule. Okay. So the antiderivative of u is going to be 1/2 u squared minus the antiderivative of u to the minus 2 is going to be u to the minus 1 over minus 1. Okay. Then we're going to plug in negative 1 and plug in negative 2. So let's keep going on that. So we've got 1/2 u squared plus 1 over u. That's what we're needing to plug into. So let's plug in there. So if I plugged in negative 1, what I would get is 1/2 minus 1 minus, and if I plug in negative 2, I'm going to get negative 2 squared is going to be 4, so 4 over 2 minus 1/2. Okay, please try to reduce as much as you can doing this stuff in your head. Because if you do a bunch of it in your head and you're trying to do all the minus signs all at the same time and everything, then you're going to get all confused. So plugging in with minus signs can be really confusing. Please don't do that. All right. All right, so I've got 1/2 minus 1 minus 2 plus 1/2. So 1/2 plus 1/2 is 1 minus 1. Those cancel each other, and the result is minus 2. That is my answer. Okay. Good. couple of other things that I want to note. We're actually going to prove this theorem, but I want to note just a couple of other things, and then we'll do a couple of other examples, and we'll actually be done for today. So this is the meat of this is an amazing, amazing theorem. So the first thing that I want to note is that this says any antiderivative. Any should kind of trigger your radar to say, well, wait a minute, could I use a different one? So for example, in this first problem, what if instead of using x squared, I used a different antiderivative? So if I did this problem, but instead I used the antiderivative x squared plus 3. Okay? Well, you'll notice if you use that, if I plug in 1, I'm going to get 4. Well, let me do it a little bit better. If I plug in 1, I'm going to get 1 plus 3. And if I plug in 0, I'm going to get 0 plus 3. And you'll notice that the 3 here and the 3 here cancel each other, and I still end up with the same answer of 1. So what you'll notice here is that when I'm looking for an antiderivative, generally, I could write the antiderivative plus c, because any antiderivative would work, but you're going to get a plus c here, and then a minus c from here, and the c's are going to cancel. So you don't, when you're looking for any antiderivative, you don't care about the plus c here. Ignore the plus c when you're doing definite integrals. In other words, you're doing an integral from a number to a number, you do not need the plus c. If it's what we call a general antiderivative, this is also known, if there's no limits, if there's no numbers on here, this is known as an indefinite integral. This is called a definite integral. Okay, if there are no limits, it's called an indefinite integral. There we have to have the plus c on there. It's very important. It's a general antiderivative. For a definite integral, don't put the plus c. You do not need the plus c. Okay? So that's one thing to note. Another thing that I want you to notice is that this is saying that differentiation and integration really are opposites of each other. They really do work both ways. That's the key message of the fundamental theorem of calculus. If f is any antiderivative, then that means that you're integrating the derivative. And what's happening here is when you integrate the derivative, in other words, if I have a function and I differentiate and integrate, I get the original function back again. So differentiating and integrating really are inverse processes of each other, which is another amazing thing there. Okay, so let's prove this. The proof is actually very short, and it obviously relies on part 1, which is why we had it. Okay. So let's prove this, and then we'll make a couple of other notes. We'll do 2 more examples, and then I'll show you a third example that you need to, something you need to be careful about here, okay? So let's let, so we're proving fundamental theorem of calculus part 2. Let's let g of x be the area from a to x under f of t dt. Okay. One of the things that we proved in part 1, so from fundamental theorem of calculus part 1, the derivative of g is little f, right? G is an antiderivative of little f. G is an antiderivative of little f. Okay? Now let's let capital F be any other antiderivative of little f. One of the things that we know about antiderivatives is that if you have two antiderivatives for the same function, one of them is the other one plus a constant, right? Okay. So we know that any other antiderivative is going to be this thing plus a constant. So now I want you to notice something. Let's try plugging A into this function and see what happens. We get the area from A to A under this function. And what is the area from A to A? That's just 0, right? Okay, well, what happens when I plug in B? If I plug in B, I get the area from A to B. Okay, so here's where we get the end of the proof. If I take f of B minus f of A, well, f of B is just g of B plus a constant. F of A is just g of A plus a constant. Do you see what I did? I just, f of B minus f of A, which is my goal here, is just g of B plus a constant minus plugging in A gives me g of A plus a constant. And you can see the constants are going to cancel, right? And we already figured out that g of A is 0, and g of B is just the integral. So we're done. The integral, again, it doesn't matter if I'm using t or x, all of that's the same, is f of B minus f of A, the antiderivative with B and A plugged in. So that's it. Wow. So the goal, the thing that the kind of final word that the fundamental theorem of calculus tells you is that if you want to evaluate antiderivatives, you have to find an antiderivative. If you want to evaluate integrals, the way that you should go about trying to do it is to find an antiderivative. If you can do that, all you have to do is plug in. So the goal in all of this is always to try to find an antiderivative. Okay. One thing to keep in mind, is that in order to find antiderivatives, so I'm just going to give you another example here, you have to keep in mind the stuff that we went over in section 4.1 about antiderivatives. Let me give you an example. If I want the area from negative 1 to 2 under x times x minus 1, remember that if you have a product, you cannot just antidifferentiate each part. We don't have nice rules for the antiderivative of a product right now. What you have to do, you remember what we did here? What did we do to find the antiderivative before? We would multiply this out, so we would get x squared minus x. And then each of these we can find an antiderivative for. So x squared came from x cubed, but we need a 1/3 there, so that when we differentiate, there's no constant in front. And then x came from x squared, but we need to do the same thing, so 1/2 x squared. And again, I could put the plus c on there, but it doesn't matter, and if it doesn't matter, I'm not going to do it. So let's not do that, but I'm going to plug in 2 and plug in negative 1. So if I plug in 2, I'm going to get 8/3 minus 4/2 minus, now let's plug in negative 1. Negative 1 cubed is negative 1. I get negative 1/3 minus 1/2. So in other words, I get 8/3 minus 4/2 plus 1/3 plus 1/2. So I get 8/3 plus 1/3 is 9/3 or 3. Negative 4/2 plus 1 is negative 3/2. So I get 6/2 minus 3/2 is 3/2. That is my answer. Okay? So keep in mind when you're trying to find antiderivatives, you're always looking for you're always looking for the methods that we used previously. So let's do another one. What if I wanted the area from 0 to 1 under e to the x? Okay, where all of your antiderivatives that you were using previously can come out here. So all I have to do is find an antiderivative of e to the x. So in other words, what differentiates to e to the x? And the answer you should give me is e to the x. You could say e to the x plus c, but we don't need the plus c here. And then we're just going to plug in 0 and 1. So I get e to the 1 minus e to the 0. E to the 1 is e. Anything to the 0 is 1. So that is my answer, e minus 1. Okay. Got it? So your homework, which is on page 284, and again, it's on that sheet that got handed out yesterday, is going to cover the second part of the fundamental theorem of calculus has number 6, 7, 10, etc. Those are going to be where you're finding an antiderivative and plugging it. That's your job. Okay. One thing to notice here, two last examples I want to give you. First one is if I were to give you the area from 1 to 2 under natural log. There's one thing I want you to notice here. We do not have an antiderivative for natural log right now. So in other words, we don't have a way to do this problem other than trying to use rectangles and approximate, which is ugly. Okay, most all of the problems that I give you won't be like this, but we do not right now have an antiderivative for natural log. So I do not have a way to do that problem right now. Okay, it's just a note is that there are many problems that we have where we don't know how to do that antiderivative. So just be careful of that. One other thing to be careful for. Let me do one last problem here, and I'm going to make a mistake, and I want you to find the mistake. Okay. So I want the area from -1 to 1 under 1 over x squared dx. Okay. The function 1 over x squared. I want the area from -1 to 1. So the first thing I'm going to do is I'm going to write it as x to the -2. And that's going to let me find an antiderivative. So the antiderivative of x to the -2 is going to be x to the -1. I add 1 to the power. But then I have to divide by that -1. Okay, notice if I differentiate, the -1 comes down and cancels, and I subtract 1 gives me x to the -2, so that's the right antiderivative. I'm going to plug in -1 and 1, so let's clean that up a little bit. This is negative x to the -1 is 1 over x. From -1 to 1, so let's plug in 1, I'm going to get -1. Minus, let's plug in -1, and I'm going to get 1. And -1 minus 1 is -2. Okay, something is very wrong with what I just did. Did anybody catch it? I'm going to give you a minute to think about that. Just give you a minute to talk about it for a second. What did I do wrong? I did something wrong. Okay. This function is not continuous on that interval. This piece is a very important assumption. The function has to be continuous in order to do what I'm about to do here. Notice 1 over x squared actually looks like this. So the function's positive on the interval that we're talking about, and we should end up with a positive area, and we ended up with a negative number. Something weird happened, and what ended up happening was that I had a discontinuity there right at 0, and I was trying to ignore it and just do this process. You cannot. If I gave you this problem, I would not want you to write all of this stuff. I could give you this as a true-false problem, and you'd have to catch my mistake. If I just gave you this problem right here, I would not want to see any of this. What I would want to see is a statement like 1 over x squared is not continuous on -1 to 1, so this this integral is not defined. Okay? It's not defined. We did not define integrals. We did not define areas for functions that are discontinuous. You're not allowed to do them right now. Okay? So hopefully that makes sense. Take a look at the homework from section 4.4. I think you might have some time here still. And have a great weekend, and we will connect again on Monday. Take care. Oh, one other thing I just wanted to point out. Today's date is 2/22, and there was a young man who discipled me when I was in college, and his favorite verse was 2 Timothy 2:2. And whenever 2:22 would come up, he would always notice it. And so since he did that, I do that too. And I notice 2 Timothy 2:2. And so I just wanted, in case you've never heard of that verse, I'd really encourage you to look up that verse. The verse says, "And the things that you've heard me say in the presence of many witnesses, these tell to, or impart to faithful men, faithful people who can teach others." In other words, this was Paul's way of telling Timothy, the things you've heard me say, teach to faithful people who can themselves teach other people. This is the process of discipleship. Okay? Teaching others to teach others about what it is that you've learned about Christ. So just a thing that I want to note, since today's 2/22, I wanted to throw that note out there. Have a great weekend, everybody, and we'll see you on Monday.